Well, what are the effects of radiation on life? We talked a little bit about how it can damage tissue and stuff. There's different types. One type of damage is called acute radiation damage. And this is where there's a large exposure within a short period of time. The main sources of this would be nuclear bombs, which thankfully those don't happen very, very often, or exposed nuclear reactor cores. And also that doesn't happen too often. So your chances of experiencing acute radiation damage are pretty small. But what happens here? Well, you get a large number of cells that die because they're just completely overwhelmed by the radiation. It's mostly the cells that are reproducing rapidly, and so it's the immune system cells and the intestinal lining. And so the main symptoms that are seen in people who are exposed are a weakened immune system and an inability to absorb nutrients. So, you can eat food, but your body just can't absorb the nutrients from it. It is possible to recover from a mild case, but the more extreme cases usually result in death, and it's usually due to infection. It's not that the radiation killed you directly, but it weakened your immune system so badly that any little infection comes in and gets here. Radiation exposure can also cause increased cancer risk. This can happen from lower doses of radiation over longer periods of time. And this happens because radiation can damage DNA, which is a molecule. Normally, DNA damage will kill affected cells, or the other types of damage to the cell will kill the cell, but sometimes it causes a defect in the DNA that causes cells to grow out of control, and that's what we call cancer. It's cells growing out of control. Cancer risk increases with radiation exposure. The more radiation you're exposed to, the greater the increase in cancer risk. But because we're dealing with human beings and there are so many causes of cancer, you can't establish an absolute threshold that says, well, yeah, I mean, we don't have anybody volunteering for these, these studies, and you would need lots and lots of people say, oh yeah, I'd like to be exposed to radiation and see if I get cancer. Yeah, not happening.
They used to do things like that without letting people know.
A long time ago, they used to do that with prisoners and stuff, and that's now recognized to be very, very unethical, very frowned upon.
Tell us what they did to get in.
Well, this is true, but we are not discussing that any further. Another problem that can happen is genetic defects in future generations. So if DNA in an egg or a sperm is damaged, that can cause the offspring to have abnormalities. This has been demonstrated in laboratory animals, but it has not been verified in humans. Even in studying survivors of Hiroshima who were exposed to large amounts of radiation, there have not been any studies that really verified that this could happen in humans. But the fact that it happens in laboratory animals suggests that it's certainly possible in humans as well.
The hills have eyes.
Pardon me?
The hills have eyes.
The hills have eyes.
Oh, God.
I'm not familiar with that. I'll have to Google that later. No? Okay, I won't.
No.
I have seen pictures. My husband's of Japanese descent, and so I probably know more about that whole situation than the average person. How is radiation exposure measured? This is trickier than you might think. Measuring mass, no big deal. Pick a unit, you need a balance or a scale or something, and you can measure the mass. There are different ways to measure radiation. The most straightforward way is just to measure the number of decay events that a person is exposed to. So a unit that's used for that is the Curie. The abbreviation is capital CI. And a Curie is 3.7 times 10 to the 10th decay events per second, which seems like a really high number, but when you think that each decay event is most likely from one atom, and then it's not really such a large number. This is not a great measure of how dangerous your exposure is, because different types of radiation cause different sorts of biological damage. So you have the gamma rays the motorbikes of radiation that have great penetrating power, but low ionizing power. And then you have alpha emitters at the other end that are like Mack trucks, and they ionize tremendously, but they don't penetrate much. So it really depends on what kind of radiation you're dealing with. So a better way, but not the best one, is to measure the amount of energy that's absorbed. And so units for that are grays and rads. A gray is a joule per kilogram of body tissue. That turns out to be kind of a large unit, and so rad, which is short for radiation absorbed dose, is 0.01 joules per kilogram of body tissue. The amount of energy that's absorbed by the body tissue. But it still doesn't account for the amount of damage. It gives you the energy, but because gamma rays go through you so well, the damage that they cause is actually spread out. Their energy is dispersed as they go through tissue, whereas alpha emitters do not penetrate, and so wherever they're releasing their energy, it's released in a more concentrated, a more dense form. So again, doesn't really give us a good comparison of damage across different types of radiation. So they use something called the biological effectiveness factor, or I forget what this stands for, RBE. I didn't have room on the slide for it. It couldn't just be the same. That would be too easy. It's the relative biological effectiveness. Relative biological effectiveness, or the biological effectiveness factor. It's just a correction factor. So different types of radiation are going to have a different RBE. So you take the dose in rads, you multiply it by this radiation biological effectiveness. Did I get it right? And that gives you a dose in REMS. So REM is Röntgen Equivalent Man, REM. So this is correcting the energy for the kind of damage that it causes in humans. So different types of radiation are going to have a different RBE. So the RBE for alpha radiation is going to be much higher than for gamma because it causes a more dense energy in the tissue than a gamma ray does. And thankfully, we're not going to do any calculations with all those units. But there they are. This is an interesting table. Exposure by source for persons living in the United States. So natural sources of radiation, 5-hour jet plane, cosmic radiation. I mean, you could argue, how is a 5-hour jet plane ride natural? The jet plane ride isn't natural. It's just that when you go up into the atmosphere, you're exposed to more stuff. Cosmic radiation from outer space, wearing a tinfoil hat's not going to help with that. Terrestrial radiation, stuff coming up from the ground. Natural radionuclides in your body. We talked about radiocarbon dating, right? And how all living organisms contain some carbon-14. Well, that's a source of radiation that you're exposed to, radon gas. And so here are the doses. Terrestrial radiation, 28 millirems per year, and that's over your whole body. Radon gas is actually the highest of the natural sources, 200 millirems per year, but that's just a dose to your lungs. Now, if you don't have a basement in an area that has naturally occurring radon gas, you're probably okay. Who knows what happened when I was growing up in Iowa? They do have that there. Diagnostic medical procedures. So these are, you go in and have a test done, you're going to be exposed to some radiation. Things you probably have more often are dental x-rays. The panoramic or the bite wings, 30 to 80 millirems. That's the skin dose. Mammogram, barium enema, upper GI.
What's a barium enema?
A barium enema. They, well, you know what an enema is, right?
Yeah, so
okay, so it's got barium in it, and then it goes all around you, and then they can then see what's going on with your bone marrow. Yes, it's lovely. I personally have not ever had that done, and I hope to never have that done.
It gives it to your bone marrow.
Yeah, and then they can see. And we're going to talk about some of these diagnostic medical procedures in the next section. Consumer products, building materials, luminous watches, tobacco products. So somebody who smokes 30 cigarettes per day, 16,000 millirems per year. That's just like way higher. Until I looked at this, I did not realize that smoking tobacco exposed you to more radiation. Did you know that?
Yeah.
Did you? Good for you. I'm glad somebody knew that. That is not something they're publicizing on television. People are all bent out of shape about radiation, but nobody mentions that.
Does it come from the light of the cigarette or just the cigarette, the tobacco product itself?
It must be from the tobacco product itself. I'm not exactly sure. That would be something to look into. Yeah.
It doesn't mention anything about people who chew tobacco.
It doesn't mention about chewing, but they're not giving everything here. These are selected things. So the range here is from 0.04 millirems per year to 16,000 millirems per year. So when does this exposure become dangerous? A lifetime of exposure to natural sources, probably radon excluded, is not going to cause significant health effects in humans. When I looked at that other chart and then I looked at this, I was like, wait, what? 20 to 100, but look, this is REMS. Those other ones were millirems, okay? 16,000 millirems is 16 rems. So smoking cigarettes, 30 a day, is getting you up into this place where you're probably going to have decreased white blood cell count and possible increase in cancer risk. So that's probably one of the mechanisms that results in smoking causing increased risk of lung cancer, right? 100 to 400 is where radiation sickness is observed. And then above, 500 and above, death. 500 is going to take a while, 2 months. 1,000, often within 2 weeks. 2,000 REMs, you're dead within hours. That's a good question. I don't know the answer. What sort of dose did people exposed at Chernobyl or Hiroshima experience? I don't know that off the top of my head, but that's an interesting question. We should look that up.
How many sieverts are in a REM?
How many sieverts are in a REM? In the margin of your book, it gives that relationship. 1 REM is 0.01 sieverts. The sievert is the SI unit, but the United States, we're just stuck in, so we're still using REMs.
Do you know where this chart came from? Because I was seeing conflicting results from the physics class chart that had like this.
Interesting. I do not know where this chart came from other than the 3rd edition of Tro, which is exactly where it came from. There certainly could be variations. It's certainly open to interpretation. I think this is intended to give us just a ballpark idea of what sorts of levels are going to cause different effects. Again, because we can't really study this very well, the opportunities for study are limited, and so then the data is not as great as one would like. Any other questions?